Now, let's see how we can implement the word-to-vec algorithm using the GenSum library, starting with the installation. To do this, you will need to run a simple pip command to install the GenSum library, which is really well suited for natural language processing tasks. Next up, we'll create a small sample corpus of sentences to train our model. These sentences will contain various references to royalty, ensuring there's enough context for word relationships. After defining our corpus, we'll tokenize the sentences. This means breaking each sentence down into individual words using the NLTK library. Now, this tokenization step is crucial because the word-to-vec model requires an input format where words can be processed in context. Now, let's implement the word-to-vec model using our tokenized sentences. In the parameters for the word-to-vec model, we'll specify the size of the word vectors, the maximum distance between words in the context window, and the minimum word frequency for inclusion in the model. Once we train it, we'll retrieve the vector representation for the word king, which will beautifully illustrate how word-to-vec converts words into meaningful numerical representations that, guess what, capture relationships and contexts. Now, let's dive into implementing the skip-gram model using the word-to-vec algorithm. In this segment of our tutorial, we're going to train the model by passing in our tokenized sentences along with some specific parameters to control various aspects of the training process. The vector size parameter is crucial as it determines the size of the resulting word vectors. Then we have the window parameter, which defines the maximum distance between the target word and its surrounding context words. This way, we can specify just how much context we want to consider. Now, setting the min count parameter to 1 is really important because it ensures that all words in our dataset are included in the model, even those that appear just once. But the key highlight here is the SG equals 1 parameter, which instructs the model to use the skip-gram approach. Once we've trained the model, we'll use the similar by word method to retrieve words that are similar to king. This method fetches a list of words that share similar contexts, reflecting the relationships we've captured during the training phase. Finally, we'll print out the results, showcasing how words like queen, prince, and throne naturally cluster around king. This really demonstrates the power of word embeddings in capturing those nuanced semantic relationships. The displayed chart is a horizontal bar plot titled Performance Features of Word-to-Vec. Here, it quantifies 5 features with performance scores on a scale from 0 to 100. Predictive skill at 85, contextual understanding leading the charge at 90, dimensionality reduction at 75, efficiency at 80, and flexibility ringing in at 88. Let's dive into these results a bit. Right off the bat, we see that contextual understanding shines the brightest with a score of 90, which tells us that, among all these features, word-to-vec excels in capturing those all-important contextual signals. Following closely, we have flexibility at 88 and predictive skill at 85. This indicates that word-to-vec is not only adaptable across various tasks, but also reliably predictive. Pretty neat, huh? Efficiency comes in next at 80. It's solid, sure, but a touch lower than the adaptability and predictive capabilities we've just discussed. And then there's dimensionality reduction bringing up the rear at 75, which creates the most significant gap, 15 points, when compared to our top feature. So, to sum it up, according to the chart, word-to-vec's main strengths are in contextual modeling and adaptability, but it does have a relative weakness, albeit not a negligible one, in dimensionality reduction compared to those other attributes we measured. The numeric labels at the ends of each bar nail down these scores for us, while the x-axis extending to 100 helps us compare the magnitude of these differences directly. It all really illustrates how word-to-vec operates, doesn't it? Now, let's implement the following to visualize our word embeddings using TSNE. First, we need to install the matplot library, which is going to help us create some eye-catching plots. This is really straightforward. You can do it with a simple installation command. Once that's done, we'll import the required libraries. Remember, we'll need matplot library for visualization and tsne from scikit-learn for dimensionality reduction. So, what's next? We'll retrieve the word vectors generated by our skipgram model. Here's how. First, we create a list of words from the model's vocabulary, and then we use that list to extract their corresponding vector representations. Pretty neat, right? Now, applying tsne will allow us to reduce these high-dimensional vectors down to just 2 components. This makes it much easier to visualize their relationships in a 2-dimensional space. Now, let's plot those results. We'll set the figure size to ensure everything is clear and neat, and then scatter the tsne output on a graph. To help you better understand what you're looking at, we'll annotate each point with the corresponding word label. This way, it'll be much easier to see their distribution. Finally, we'll label the axes properly, add a title to the plot, and don't forget to display a grid for better readability. After executing this code, we'll get to observe how similar words, like king and queen, group together, visually reinforcing those semantic relationships we discussed. As useful as word embeddings are, it's essential to be aware of their limitations. For one, they don't quite capture context-dependent meanings. Take the word bank, for instance. It could refer to a financial institution or the side of a river, right? Well, word embeddings struggle to differentiate these meanings based on context, which can lead to misunderstandings in AI applications. And that's where contextual embeddings step in. Models like BERT and Elmo generate representations based on the context of a given sentence, effectively addressing the shortcomings we see with traditional word embeddings. While word embeddings like word2vec offer significant benefits in terms of efficiency and simplicity, they may not be suitable for the nuanced understandings required in many advanced NLP tasks. Today, we've dived into the fascinating world of word embeddings and explored how the word2vec algorithm constructs these vector representations of words. We implemented different models, learned how to find similarities, visualized these relationships, and even discussed the limitations of classic embeddings. Now, as you continue your journey in AI and NLP, leveraging these concepts will be crucial for building intelligent systems that can truly understand and process human language effectively. Remember, the ultimate goal of machine learning and AI is to develop tools that comprehend the rich complexities of language, bridging the gap between human communication and machine understanding. So, thank you for joining me in this exciting exploration of word embeddings.